Now, I've seen that people have shown you during the day quite a lot of hardware, rockets taking off and this and that inside of spacecraft, and that you also heard a lot about software from the brilliant young people who are here. So I thought that I would try to be a little different and to tell you something about the science that is behind this particular mission. So let us begin by talking about comets. Now, Leo mentioned that I was involved earlier with the Giotto mission to Comet Halley, and I was responsible that time for the Irish experiment called Epona, and we flew through the head of a comet in great speed, and this photograph was taken in March of 1986. So what is this big black object here in space? Well, we can tell that a comet nucleus is an amalgamation of dust, ices, and frozen gas. And these were formed at the time of the formation of the early solar system, very, very far away from the sun. And so, because they're in a kind of a deep freeze, they have maintained the composition of the material out of which the solar system was formed. And so this makes them a very interesting target of opportunity to go there and study. Now, at the same time, when the Earth was formed, it was probably too hot to retain volatile materials, and there's a very strong theory that at least part of the organic materials that were decisive for biological and chemical evolution here on Earth were carried there by comets during the period that is called late heavy bombardment. So it was decided a mission should go there and study a comet and try to find out, first, is this the situation? Can we really identify the material from which the early solar system was formed, and say something about perhaps that comets brought prebiotic molecules to Earth. So here is the spacecraft, this Rosetta. And one of its big objectives is to monitor the evolution. The comet has a terrible name, 67P Churyumov-Gerasimenko. So it took me a week to learn how to say that. But I'll just call it 67P for today. And it is escorting the comet, this spacecraft, over an extended period as it follows a trajectory that goes initially towards the sun, and that's what we have going on now. And then later, after the middle of August, it will start moving away. And then the other big thing was to analyze data from an active lander, our little Philae, deployed onto the surface. So we have a first here. Rosetta is the first spacecraft to investigate from close proximity how a frozen comet is transformed as it flies towards and away from the sun. And in that regard, the chemical, mineralogical, and isotopic compositions of the cometary atmosphere, which is called coma, are monitored continuously. And that allows the chemical reaction chains whereby the coma species are produced from the original icy material down on the nucleus to be identified and quantified. Now, it's important that I should point out that it's not possible to make a detailed inventory of the organics present on a comet nucleus through making observations from the ground. And you can't even do it by making flyby observations like the Giotto mission to Comet Halley. And that is because the materials that are present in a comet's atmosphere are already chemically differentiated from their parent substances by the time that you can see them in the cometary atmosphere. So here is the solution. Rosetta's lander Philae was designed to land on the nucleus of 67P, where it can support drilling below the comet's surface to bring up for analysis pristine samples of the material from which the solar system was formed. And here on the left, you see little Philae, and on the right is the Rosetta spacecraft as they were being integrated together prior to flight. Now, there are 10 experiments on the lander. So as I've been given just a little bit over 10 minutes to talk to you, I can't tell you all about that. But I'll tell you the one that's closest to my heart, and that's Cosac. I'm very much involved in this one. People say it's about the size of a small washing machine. And Cosac consists of a gas chromatograph and a time-of-flight mass spectrometer with some auxiliary systems that help to operate. And the idea is that samples from the comet's surface can be sealed in an oven, and the resulting gas is then passed on to Philae. And there, the two parts of the instrument acting together have the capability to detect and identify complex organic molecules in the cometary sample from their elemental and molecular compositions. So here then, we have something really exciting. Identification in the cometary sample of the fundamental organic building blocks of life, and we're talking here about amino acids, nucleic acids, and so on, that can support the theory that comets were responsible for seeding the Earth with prebiotic molecules. It's an important question to ask Mother Nature. And in addition, the presence of simple molecules identified to be at the origin of chemical reaction chains that produce more complex molecules of biological interest can be highly relevant to understanding the early chemistry of life. Now, Leo mentioned the Irish electrical support system. And how that works is that commands from the spacecraft to the instruments on the lander are transmitted by RESS, which was designed and built by my group, Space Technology Ireland, out in Maynooth. And the figure there shows you one of the electronic boards that are inside. Here you see the whole unit, and very importantly now, data from the individual experiments aboard the lander during both the cruise phase from the Earth out to the comet and right now on the surface of the comet are handled by the ESS, which can receive and store them prior to their transmission to the Earth. Now, as you can well imagine, all the success of the lander depends on the successful acquisition of scientific data. So for this reason, the ESS is called, as Leo mentioned, mission-critical hardware. Without it, they have no data. This is a scene 10 years ago, a little over 10, when the spacecraft Rosetta was launched with the idea that some 10 years later, we would depose the lander on the surface of the comet. It was a very busy cruise phase going out. As you can see the orbits there, there were 3 Earth flybys, one flyby of Mars, and we visited 2 asteroids. So there was lots and lots of data and important scientific information secured before we ever got to the comet. That's an artist's view of the spacecraft coming in, and there were very sophisticated techniques which were applied. There were 8 burns followed by 2 comet orbit insertion maneuvers and all sorts of fancy orbits in order to get the spacecraft into an orbit about the nucleus at a height of about 30 kilometers. And there was a relative velocity between the two of about 1 meter per second, something like stepping off an escalator in Disneyland, that sort of thing. Now, given the extreme difficulties which were involved, because as we heard earlier, this nucleus is emitting, and we can't predict when, prodigious amounts of dust and gas, which would make a drag on the spacecraft. Getting it into an orbit like that was really an outstanding achievement. And it shows that the European Space Agency, in their dynamics team, is right on top of their game. World class. This is the nucleus. I don't have time to tell you much about it, but you can see how complex it is. There are 5 different materials there, all sorts of features, pits and mountains and craters and I don't know what. That side is called the head. It looked a bit like a duck when we saw it first. Then there was the neck part, and the other lower down is what's called the body of the comet. Now, we wanted to select a landing site. There were lots of criteria. One, of course, was that there should be good solar illumination. You can't take any pictures in the dark. We didn't want it to be too rough for Philae coming down. There had to be good visibility between the orbiter and the lander so that the signals could be passed back and forth, and so on. Here on the left side, you see a mosaic of candidate landing sites so that they were looking at each one, and in particular in terms of the illumination profile, which is shown over on the right side in color. As a result of that kind of analysis, there were 2 prime landing sites selected. One was site J on the head of the nucleus, and the backup option was the site C, which was on the body. Here we see Philae falling down towards the nucleus. It was pushed off by the Rosetta orbiter using an adjustable ejection device with separation velocity 19 centimeters per second. And the mechanical support system and Ireland's electrical support system, ESS, performed that delicate operation flawlessly. So we were so very glad to see this coming down in good order. This is an artist's impression of the lander arriving at the surface with its 3 legs outspread for a soft landing. Now, at touchdown, we expected that 2 harpoons would be fired to anchor the lander, and there would also be a cold gas system activated so that there would be no bouncing. But in the event, neither of those 2 systems worked at all. The landing gear, meanwhile, was configured to absorb most of the impact energy, and there was a screw in each foot which was to provide fixation points to the ice. And if you look up there at the 2 top pictures, you can see 3 little dots, which is the signature of where the lander landed. But it didn't stay there very long. In fact, it bounced and went up about 1 kilometer and started on a rather chaotic journey across the cometary landscape. Now, during that ascent phase, while cometary material was dislodged, thrown up into the sky, it entered into Cosac. It was like automatic digging. And all this material went into our instrument, and we got a wonderful particle spectrum. And we were able to announce that we had seen organic molecules, including carbon and hydrogen, on the surface of the comet. That picture there shows you just a shadow of the dust cloud that was thrown up. Finally, Philae, having touched down twice, crashed into the side of a crater and finally come to rest in a cave. We see here where it landed, and this place was very heavily shadowed. So all of us knew that the battery could be expected to run down very quickly. And so we formed a council of war, said, what will we do? And we decided that we would continuously implement science at the site with the participation of all the 10 instruments while the resources lasted. And we also made another quite important decision, and that was to rotate the lander by 35 degrees so that later on the sun would illuminate a longer portion of the solar cells. The primary battery powered the instruments for about 60 hours. So there was a terrific take of scientific data with many pioneering observations. And then when the battery ran down, Philae went into a hibernation. And it was canted at an angle of about 30 degrees. One foot was touching rocks out in front. Another one was pointing up into the sky, and there was a huge cliff behind. And this cliff had the effect of restricting illumination onto the solar panels. We only had 90 minutes of sunshine per 12.4-hour comet day. The comet rotates at that cadence. So there were two requirements then for Philae to wake up. Its internal temperature had to be above minus 45 degrees. Now the comet is very much colder. And also it should receive more than 5.5 watts of power. On top of the lander, there are two rectangular solar absorbers. They transform light into heat and can bring up the temperature above the threshold minus 45 degrees. Now, at the latter temperature, a mechanical switch is designed to operate, and that allows the batteries to start powering up, given that we start from 5.5 watts. When 9 watts are available, Philae can switch on its receiver, and it can start listening for a signal from Rosetta from the ESS. And when we've got 19 watts, Philae can switch on its transmitter and send a signal to Rosetta. And as Leah said, on the evening of Saturday, 13th of June, the Rosetta orbiter received from Philae via the Irish ESS an 85-second transmission, which indicated that the lander had recharged its backup batteries sufficiently to communicate. Hello, Earth, it said. And there was an indication that Philae had actually woken up much earlier, but the geometry was not right. That's probably the reason why we didn't pick it up. And already it was way up above the 19 required watts. It was at 24 watts of electrical power, and all ready for diagnostics and the resumption of operations. At the present moment, There is a lot of work going on back at the station. You saw Larry there on the television telling that they're trying to get in touch again with Philae. They will have to put the lander into an optimum, or not the lander, the orbiter, into an optimum orbit. It needs to arrive where it has a good view down of the lander at noon, just after noon on the cometary day, and it has then about 45 minutes to make contact. We, meanwhile, are very excited about the science. Cosac will now undergo extensive testing because we don't know whether the chips have been deteriorated in the very, very cold conditions that pertained out there for the last 7 months. And if everything is right, then if it works, analysis of the data coming back from Cosac can determine if prebiotic molecules are present on 67P and also provide insights into the complex chemistry whereby life can develop. So I watch this space. We're all waiting in anticipation.